Hello, my name is Paul Geyer, and I'm here to chat with you today about controls for steam power plants. This is what I'll be talking about today, the different types of controls, the safety devices, control loops, flow meters, pressure gauges, temperature sensors, transmitters, recorders, controllers, operators, positioners, and then the control room. And by way of introduction, this is just a little bit about me and what I've been doing for the last few decades. There are basically three types of industrial instrumentation systems for power plant control: analog, microprocessor, and computer. The analog control is the representation of numerical quantities by means of physical variables such as current, air pressure, voltage, rotation, resistance, electromagnetic field, etc. Analog control over the last 30 years has consisted primarily of two types: pneumatic, the use of air pressure or other gases occasionally as the power source to represent numerical values, and electronic, the use of current, voltage, resistance, EMF, etc. as the power source to represent numerical values. Microprocessor-based control stations are a digital standalone single controller type or a split architecture control system offering powerful configurable control capability on a modular basis. These units can accept standard analog electronic inputs plus digital inputs and give analog outputs plus digital outputs. By connection to a data highway for communication, other operator interfaces are easily added. Direct digital control or supervisory control computer systems, DDC, direct digital control, can perform all of the control functions, operator displays and graphics, reports and calculations for efficiency and controller tuning, or a computer can be used as a supervisory control for analog control system, microprocessor-based control units, or as a data logger with graphic displays. Choice of analog versus microprocessor-based control units or computer, DDC-SC, should be based on relative cost and future requirements. Consideration should be given to the ability to readily interface to or add to a utilities, energy management system, or other computer networks. With regard to pneumatic control systems, they should only be considered when adding to an existing power plant already equipped with pneumatic control instruments. The types of control systems available are on-off, single-point positioning, parallel metering system with oxygen trim, carbon monoxide trim with coal, steam flow metering system. Boilers should have oxygen trim in order to optimize fuel usage. Carbon monoxide trim should be considered for larger boiler installations as an adjunct to oxygen trim for increased efficiency, especially for coal firing. Maintenance and calibration is a necessity regardless of the type of control equipment being used. Pneumatic instrumentation will require more maintenance because of its usage of air that contains dirt, moisture, oil, and other contaminants than its electronic counterparts. Also, pneumatic instrumentation will require more frequent calibration checks because of its inherent mechanical linkage design versus solid-state electronic units. Now, with regard to the steam power plant controls, first, combustion control. Combustion control comprises a series of devices on a boiler developed to satisfy steam demands automatically and economically by controlling furnace combustion rates through adjustments of the burning components while maintaining a constant set point such as a fixed but adjustable pressure or temperature and an optimum adjustable ratio of fuel to air. For the metering type, proportioning plus reset plus rate action, see Figure 1. B, combustion safeguards. C, refer to the ASME Boiler and Pressure Vessel Code, Section 7, subsection C6 for minimum basic instruments required for proper, safe, efficient operation. And D, see tables 1, 2, and 3 for typical lists of instruments. For steam temperature control, critical temperatures should be recorded and also alarmed. An automatic fuel trip device is required for steam temperature out of normal range. See Table 2 for temperature sensing devices. Figure 1 indicates a typical combustion control system schematic. Table 1 indicates a list of instruments on control panels, typically the pressure elements, the draft elements. Table 1 is continued on this slide. And Table 1 is continued and concluded on this slide. Note that the designations used in this table are A, necessary, B, desirable but not necessary, C, necessary in some instances but not in others, and D, necessary but not necessarily on located panel, and E, alternate to some other instrument. Table 2 indicates sensing elements for controls and instruments. First, the flow sensing elements are indicated on this slide. On this slide, Table 2 continues, and the temperature sensing elements are indicated. Table 2 continues, and the temperature sensing elements are indicated on this slide. And the pressure sensing elements are indicated on this slide, part of Table 2. And Table 2 continued with elements for level, motion, chemical, physical, and electric and electronic sensing are indicated. Table 3 indicates locally mounted instrumentation. Continuation of Table 3 indicating thermometer and level sensing elements. With regard to feedwater control, for small packaged boilers and boilers with constant loads, a single or two-element feedwater control system will suffice. Larger boilers and boilers with widely fluctuating loads should use a three-element type. An automatic fuel trip device is required for low drum water level. With regard to steam turbine generator control, steam turbine control should be supplied by the turbine manufacturer. With the rapid advancement of electronics and electro-hydraulic control, EHC system is desirable over an all-mechanical system. The EHC system is more versatile and faster responding, which gives improvement in control reliability and accuracy, which is manifested in improved turbine performance. The mechanical hydraulic control system, MHC, has not been used since the late 1970s. Many are still in use, but they are, for the most part, not currently manufactured. Automatic startup and shutdown is easily done with microprocessor-based control equipment. A standard EHC system is comprised of four primary functions: speed control, load control, flow control, and trip. With regard to safety devices and interlocks, safety devices such as boiler shutdown devices, startup and shutdown interlocks, and alarms should be installed as recommended by the equipment manufacturer. Coal, oil, and gas-fired boilers can have different shutdown safety trips. Check the boiler manufacturer's recommendations and the ASME Boiler and Pressure Vessel Code Section 7 for standard trip conditions. Safety controls for boilers are needed for protection against explosions and implosions. Criteria for protection against boiler explosions have been well established. Protection against boiler implosions is not so well understood. For a boiler, implosion would be the result of a negative pressure excursion of sufficient magnitude to cause structural damage. Boiler implosions are caused by one of two basic mechanisms. First, the induced draft fan of a balanced draft boiler is capable of providing more suction head than the boiler structure is capable of withstanding. And second, the so-called flame collapse or flame out effect. Implosion concerns have resulted in many new control system developments. Each steam generator manufacturer has recommendations, and the NFPA has issued NFPA 85G on the subject. With regard to the control loops, a single control loop includes a controlled variable sensor, controlled variable transmitter, the controller, automatic manual control station, and final control element, including positioner, if any. Control loops used for power plants are usually of the pressure, temperature, or liquid level type. With regard to pressure control loops may be used for control of boiler pressure, deaerator pressure, auxiliary steam pressure, building heating steam pressure, and fuel oil pressure. For control of boiler pressure, the final control element regulates fuel flow to the boiler in response to boiler drum steam pressure. For other pressure applications, the final control element is usually a pressure-reducing control valve which regulates in response to downstream pressure. Temperature control loops may be used for control of steam temperature from boilers or de-superheaters and fuel oil temperature from fuel oil heaters. Liquid level control loops may be used for control of boiler drum water level, condenser hot well water level, feed water heater drain cooler water level, and deaerator storage tank water level. With regard to flow meters, particularly differential pressure type, have remained unchanged over the past decade. There have been several new types of flow meters added to the flow measurement arena. The new meters, such as Vortex, Ultrasonic, and Doppler, have added improved accuracy, linear signals, and rangeability as high as 16:1. With the improvements in electronic transmitters over the past decade, there has been an improvement in their overall specifications. However, the differential pressure type flow meters have remained the same. The accuracy is 2 to 3% and rangeability of about 4:1 maximum. The cost of electronic transmitters are now lower than pneumatic counterparts and should be used except for all pneumatic systems. For the types of flow meters, see Table 4. And for their applications, see Table 2. Pressure gauges are usually direct connected and field mounted. Size and ranges are specified by user. Local mounted gauges give a backup reading and also help operators in determining if equipment or pressure systems are working satisfactorily. Accuracy is normally 0.5 to 1% of span. For test and calibration purposes, use 0.25 to 0.5% gauges. Figure 2 indicates schematically typical control loops for pressure, temperature, and liquid level. With regard to temperature sensors, the basic type of temperature sensors are thermometers, thermocouples, and resistance temperature detectors. Thermometers are located on equipment and piping to provide local temperature indication. Thermocouples provide a reliable and accurate temperature measurement for most remote temperature sensing applications. Thermocouples can be used with pneumatic and electronic transmitters, or they can be direct connected to some instruments. Thermocouples are nonlinear. With regard to resistance temperature detectors, resistance temperature detectors offer a temperature range about the same as a copper constantan thermocouple with detection of temperature changes of 0 0.03 degrees Fahrenheit. The resistance detector does not have a reference junction as a thermocouple does, since it operates on the measured change in the resistance of a metal or semiconductor, a thermistor, with temperature. Platinum, because of its inherent stability and linearity, is becoming the standard of the industry, with some copper and nickel still being used. Copper is quite linear, but nickel is quite nonlinear. Resistance detectors can be used with pneumatic and electronic transmitters, or can also be direct connected to some instruments. Transmitters are primarily used to transmit an analog output, pneumatic or electronic, proportional to its measured signal. The American Petroleum Institute recommended practice 550 suggests for general service applications that the pneumatic tubing length from transmitter to controller to control valve not exceed 400 feet. Neither run should exceed 250 feet. Standard output signal for pneumatic transmitter is 3 to 15 psi with a 20 psi air supply and 4 to 20 milliamps DC for electronic transmitters with a nominal 30 volts DC power supply. There are options for other output signals depending upon the manufacturer. Recent electronic enhancements have made most electronic transmitters much more accurate, reliable, and smaller in size, weight, and less expensive than its pneumatic counterpart. Electronic signals are easier to adapt to microprocessor and computer-based systems and should therefore be given consideration over pneumatics. Electronic signals for transmitters are easier to adapt to microprocessor and computer-based systems and should therefore be given prime consideration over pneumatics. Materials of construction is of prime importance when selecting a transmitter. Many options are available and should be selected on the basis of need or life expectancy and cost. Most transmitters are field-mounted near point of measurement. Most electronic transmitters are the two-wire type. Sensing length lines longer than 50 feet are not usually recommended and should be used only when absolutely necessary. Where transmission line length, pneumatic, poses a problem in a flow loop, use a volume booster or mount the controller near the valve. Table 4 indicates flow meter selection parameters. With regard to recorders, recorders are primarily used to record data to provide a permanent record of present and past conditions. Selection of recording signals should be based on the following: federal and state requirements, equipment manufacturer recommendations, accounting purposes, safety requirements, and operator requirements. Recorders are available in different sizes and shapes, roll, fold, circular, and number of recording points. The selection of types should be based on suitability to needs and in particular the number of points being recorded. Trend recording is becoming more popular since it allows the selection of a large number of inputs to be recorded and for time periods as desired by the operator. Trend recording also allows for recording of critical points during startup. Most panel-mounted recorders are the 4-inch strip chart type because of space requirements. Most field-mounted recorders are the 12-inch circular large case type because they usually meet NEMA Type 3 or better protection. See NEMA Standard Publication number 250, Enclosures for Electrical Equipment, 1000 volts maximum. Recorders are normally supplied with 115 volt 60 cycle or 24 volt DC power for the chart drives. Some can be supplied with a pneumatic impulse or mechanical chart drive. With regard to controllers, controllers can be used in either closed-loop feedback or open-loop control configurations. In a closed-loop control configuration, measurement is made of the variable to be controlled and is compared to a reference or set point. If a difference or offset exists between the measured variable and set point, the automatic controller will change its output in the direction necessary for corrective action to take place. See Figure 3A. Open loop control simply does not have a measurement sensor to provide an input to the controller for a comparison. See Figure 3B. Open loop control can also occur when an automatic controller is placed in its manual position, saturation of the controller output at 0 or 100% of scale, or failure of the final operator when it can no longer be changed by its input signal. Feed-forward control is relatively new, and in most cases it is also used in closed-loop control configurations. While feedback control is reactive in nature and responds to the effect of an upset which causes an offset between the measured variable and set point of the controller, feed-forward schemes respond directly to upsets and thus offer improved control. See Figure 3C. There are also several types of control units available, such as ratio control, cascade control, auto select control, and nonlinear control. These units can be analog type and either electronic or pneumatic. However, additional pieces of instrumentation may be required to actually do the above types of control. With the new microprocessor-based control stations, they can perform most of the types of control listed above without additional devices and still provide 18 or so control algorithms. For standard control actions, see Figure 4. For a controller to operate correctly, the controller must be properly tuned. Each controller must be tuned for its control loop. Seldom are two alike. This can be time-consuming, but it's necessary to have correct controller response to process changes. Some new microprocessor controllers have self-tuning capability. This is a major addition for exact tuning of the control parameters to match the process dynamics. The microprocessor-based controllers should be given first consideration as they are less expensive, state-of-the-art, and can perform many more functions than a standard analog controller without additional pieces of equipment. These new units should also be considered for retrofit, as they can easily replace old electronic and pneumatic analog controllers and other devices. Some of the new microprocessor-based controllers are configured from push buttons located on the controller faceplate. Special calibrators or mini-computers are not required to configure these standalone controllers. Figure 3 indicates typical controls: closed loop control, open loop, and feed forward control. Figure 4 indicates type of automatic controller action: two-position proportional, single speed floating, proportional speed floating, proportional plus reset, and proportional plus reset plus rate. Operators are used to drive final control elements such as control valves and dampers from one position to another. The general types of operators are pneumatic diaphragm or piston electric and electro-hydraulic. Pneumatic operators, including IP converters, are the least expensive when compared to electric or electric-hydraulic type. Operators, final control elements for major control loops, should be pneumatic unless normally furnished otherwise on equipment as standard by a manufacturer. Electric operators are used prevalently in heating, ventilating, and air conditioning systems. Electro-hydraulic operators are used for high force or torque applications and in remote locations where lack of compressed air supply rules out the use of pneumatic operators. Positioners are used on control valves to force the stem and valve plug to move to a position as called for by the control signal. Positioners are used primarily to overcome valve stem friction to compensate for long pneumatic transmission lines, or when extreme or variable line pressure can offset the valve plug. Every control valve exhibits from 2 to 10% hysteresis unless it is equipped with a positioner. The effect of valve position hysteresis is indicated in Figure 5. A positioner should be used for liquid level, volume, and weight whenever a two-mode controller, proportional plus integral, is used. For temperature control, a positioner will be helpful but not essential. As a general rule, use a positioner on control systems that have a relatively slow response, such as liquid level, blending, and temperature control loops. Do not use a positioner on control systems that have a relatively fast response, such as liquid pressure, most flow, and some pressure control loop. Figure 5 indicates hysteresis caused by friction in a valve. With regard to the control room should be located in the boiler turbine area where visual inspection can still be made, but completely enclosed and air-conditioned with high efficiency filtration. Instruments should be mounted on a panel within the control room. A positive pressure should be maintained within the control room to keep dust and other dirt particles from entering. The control room should have the following: clean, dry atmosphere, relatively constant temperature and humidity, no vibration, adequate light, reliable electric power free of surges in voltage and frequency, clean, dry air of adequate pressure and capacity for pneumatic instruments, and air conditioning, which is a necessity for electronic distributive control systems and computers. See Tables 1 and 2 for typical lists of analog instruments. With the new microprocessor-based control systems, the operator interface can be a color or black and white cathode ray tube, CRT, thus eliminating the need for panels. The operator can control the boiler from a single CRT with redundant CRTs located elsewhere if desirable. Field inputs and outputs should be done through the floor or ceiling of the control room. All field measurements should come into one central control room. And that brings us to the conclusion of this brief discussion of controls for steam power plants. And I hope that this has been of interest to you and was about what you were looking for, and that you will be able to use some of this information moving forward as steam power plant projects come across your desk in the future. Again, thank you very much for letting me chat with you, and have a nice rest of the day.